Ever get curious about what galaxies looked like way back when, billions of years ago? We see those amazing James Webb pictures, but what are we actually seeing? Today, we're diving into a paper with a title that sounds more like a band name than a research paper, Panic, at the disks.
Catchy, isn't it? And the name's not far off from how astrophysicists are reacting, to be honest. This paper, one of the first to use JWST data to look at galaxy shapes, has caused quite a stir, and, well, some head-scratching, too.
So, set the scene for us. Why all the fuss? We're talking over 12 billion years ago, right? Isn't that just a blur at that distance?
You'd think so, right? But that's the magic of JWST. We're seeing those early galaxies just as they were forming with incredible detail like never before. And what we're seeing is making us rethink some old ideas.
Intriguing. Before we get to the panic part, let's get everyone on the same page. We're talking about galaxy shapes here, right? Spirals, ellipticals, all that.
Exactly. For decades, we've used what's called the Hubble sequence to categorize galaxies. It's like a cosmic family album. You've got your grand spiral galaxies like our own Milky Way, those rounded ellipticals, maybe a bit older, more settled. And then there are the irregular galaxies, the wild youngsters.
Right, and the thought was always that this sequence acted kind of like a timeline. Galaxies start off irregular and then evolve into those more defined shapes.
Exactly. But this is where things get interesting, especially when we think about how we actually see these distant galaxies.
You mean with telescopes? Isn't it all just light from really, really far away?
It is, but the kind of light we observe and how it's been stretched over billions of years makes all the difference. Take the Hubble Space Telescope. It was great at seeing ultraviolet light, good for studying stars forming and things like that. But when you're looking billions of years back, UV light alone doesn't tell you everything about a galaxy's shape.
Okay, I feel a but coming. What's this new twist in the story? What about JWST?
The key is that JWST sees way deeper into infrared light than Hubble ever could. And that infrared light, it's crucial when we're looking so far back in time.
I'm listening. Why is that?
It's all because of something called redshift. Think of an ambulance speeding away from you. Its siren seems to stretch out and get lower, right? Light's similar. It stretches as it travels across space. The farther it goes, the more it gets redshifted. Its wavelength stretching towards the red end of the spectrum.
And because the universe is always expanding, the light from those super old galaxies, which started as visible or even ultraviolet light, is stretched out so much it reaches us as infrared light, right?
Exactly. And that's where JWST's infrared vision comes in.
So it's like JWST has cosmic X-ray vision, letting us see past the redshift to what those early galaxies actually looked like.
Precisely. It's called rest frame optical observation. We're basically removing the redshift effect and seeing those old galaxies in their true light, not just their energetic afterglow.
Wow. No wonder astronomers are excited. It's like finding a perfectly preserved dinosaur fossil when we thought only scattered bones were left.
Perfect analogy. But here's the real surprise. What JWST found in those early galaxies wasn't what anyone expected at all.
Okay, now you have to tell me more. What did they find? And why the name Panic at the disks? We'll get into those groundbreaking findings and what they mean for our understanding of the universe right after this. All right, so where were we? Yes, cosmic X-ray vision and a touch of panic. What is it about these early galaxies that has everyone so riled up?
Well, remember us talking about the Hubble sequence and that whole cosmic timeline. Irregular galaxies evolving into spirals or ellipticals over billions of years.
Yeah, like a slow, graceful cosmic dance.
Well, imagine looking back in time and seeing a bunch of teenagers at the senior center already doing the waltz. That's kind of what happened. JWST found way more disk galaxies in the early universe than anyone expected.
Wait, hold on. Disk galaxies, those beautifully structured spirals. You're talking about the chaotic early universe.
You got it. Previous studies, using mostly UV observations from Hubble, found very few disk galaxies that far back. The thinking was that those spiral structures took billions of years to form long after the Big Bang.
But JWST is saying, think again.
Exactly. That's where the panic comes in. This throws a wrench into our neat cosmic timeline. It suggests that either disk galaxies formed much earlier than we thought, or, and this is even more interesting, maybe some of them haven't changed much in over 10 billion years.
Okay, no, my mind is really blown. So which is it? Early formation? Or have they just been hanging out, looking amazing for billions of years?
That's the million-dollar question. The paper looks at both possibilities. On one hand, those early galaxies might have been full of gas, which is what you need to make stars. All that fuel could have sped up the formation of those disk structures.
Like a fast-forward button for galaxy evolution.
Precisely. But then again, some of these disk galaxies could be ancient relics, untouched by the mergers and collisions we thought drove galactic evolution.
So they've been cruising through space while other galaxies are bumping into each other and making a mess.
Kind of, yeah. If that's true, it challenges what we know about how galaxies interact and evolve. Maybe those early disks were tougher, or maybe they were in quiet parts of the universe.
I'm picturing these pristine, ancient galaxies. What else can you tell me about them? Any insights into their size, what they were made of?
Well, this study was mainly focused on proving these early disk galaxies existed, which is a huge deal in itself. But the researchers did use some cool tools to take a closer look.
Like what? What kind of tools are we talking about?
One method is called morphometrica, a fancy term for quantifying galaxy structure. It goes way beyond just looking at a galaxy and saying, well, that one looks kind of spiral-ish.
So like a cosmic ruler and compass, but for galaxies.
You got it. It's all about measuring things like how concentrated a galaxy is, how tightly its stars are clustered in the center, its asymmetry, how smooth or clumpy it is.
More like cosmic fingerprint analysis than a simple ruler.
Now you're getting it. Each galaxy has a unique structural fingerprint, and analyzing these details helps us understand how they formed and evolved.
What did these cosmic fingerprints tell us about the early disk galaxies?
One key measurement they looked at was something called the STScI index, basically telling us how light is spread out within a galaxy.
Break that down for me. What's the big deal about light distribution?
Imagine shining a flashlight on a wall. Hold it close, you get a bright, focused spot. Move it back, the light spreads out, gets more diffuse.
So a galaxy with more concentrated light would have a higher STScI index, like that close-up flashlight beam.
Exactly. A higher STScI index usually means a more centrally dominated structure, like an elliptical galaxy. A lower index means a more evenly spread out distribution of stars, more like a disk galaxy.
So when they looked at the STScI indices of these early disk galaxies, did they match what you'd expect?
That's where it gets interesting. Many of them did have STScI indices around 1, which fits with them being disks. But even some galaxies that look like spheroids, those rounder shapes, also had surprisingly low STScI indices, not what you'd expect.
So some of these galaxies are like teenagers who put on a suit, but then you see those bright green sneakers, not quite what they seem.
Exactly. It suggests that even way back then, the universe was dynamic and evolving, with galaxies still figuring out their final forms.
This is seriously revolutionary. But before we get too deep into cosmic measurements, let's step back. What does it mean to find all these well-formed disk galaxies so early in the universe? What are the broader implications? So we've got these early galaxies, more stylish than we thought, but there's got to be more to it than just galaxies formed faster, right? This has to have bigger implications, right? We're talking about the fundamentals of the universe here.
Absolutely. This isn't just about adjusting our cosmic timeline. This could change how we see the whole universe evolving.
Okay, hit me with it. Give me the big picture.
Well, for one, it makes us rethink dark matter.
Dark matter, the invisible stuff that's supposed to make up most of the universe's mass. What's that got to do with galaxies from billions of years ago?
Good question. See, our current models for how galaxies form say that dark matter is essential. It provides the gravitational framework for galaxies to form in the first place, like an invisible glue holding it all together.
No dark matter, no galaxies, no stars, no us. Got it.
Right. But here's the thing. These models also predict those early galaxies should be messy, irregular, still coming together because of dark matter's pull. Finding so many nicely formed disk galaxies throws a wrench in that.
So are we saying dark matter might not be as important for galaxy formation as we thought? Or that we need to rethink dark matter itself?
Could be either or both. That's what makes this so exciting. We have to go back and look at some of our most basic ideas about the universe.
It's like this discovery is pulling back the curtain on a whole new act of the universe's story. So where do we go from here? What are the next big questions?
Well, we need to study these early disk galaxies in way more detail. This paper was just the beginning. We need to figure out their masses, how fast they're forming stars, what that star-forming gas is made of.
Like a cosmic census, getting to know these early galaxies better.
Exactly. And that's where JWST shines. Its amazing sensitivity and resolution let us study these distant objects with detail we could only dream of before.
Like going from reading about ancient civilizations to actually visiting their cities and talking to the people?
Perfect analogy. The more we learn about these early galaxies, the more we understand what shaped the universe we see today. It's all connected.
We've got time for one last question before we wrap up. We've talked a lot about galaxies in the universe, but what about life beyond Earth? Do these findings affect that search at all?
Ah, the big one. Now, this specific study doesn't directly look for life, but it does bring up some interesting thoughts.
I'm all ears. Always love a little cosmic speculation.
Well, we tend to think of spiral galaxies with their structures and relatively calm environments as more likely to have life as we know it.
Less chaos, more chances for life to start and develop.
Right. If disk galaxies were more common early on than we thought, then the right conditions for life might have existed in many more places much earlier, too.
So instead of life showing up late to the party, it could have had a much longer head start, maybe even starting in those early disk galaxies billions of years ago.
It's possible we're still a long way from knowing if there's life out there, let alone if it began in those old galaxies.
True, but it's a fascinating thought to end on. We've gone from panic at the disks to thinking about the very origins of life. I'd call that a successful deep dive.
I agree. It just shows how much we still have to learn about the universe and how each discovery can open up whole new ways of exploring.
Well said. And on that note, we'll leave our listeners to think about the mysteries of the cosmos and all the amazing discoveries yet to come. Thanks for joining us on this deep dive into the early universe.
It was my pleasure.
Ready to explore some seriously ancient history? We're talking billions of years ago, way back to the universe's earliest days.
Way before dinosaurs, way before Earth even.
Exactly. And today, we're taking a deep dive into some fascinating discoveries about galaxies, specifically their shapes. We've got a scientific paper here with a pretty intriguing title, Panic at the Disks.
Astronomers love a dramatic title.
Who doesn't? Right. So we're going to break down why this research has caused such a stir in the astronomy world. But first, let's rewind a bit. Before we can talk about what this new research reveals, we need to talk about what we thought we knew.
Setting the scene.
Exactly. So for the longest time, our best views of the most distant galaxies, the ones that existed when the universe was just a baby, came from the Hubble Space Telescope.
Hubble's a legend, for sure. Revolutionized our understanding of the universe.
Absolutely. But Hubble had its limits. It could only see so far, and it couldn't see everything. Now, with the James Webb Space Telescope, or JWST, we're getting a whole new perspective on those very early galaxies.
It's like we've been squinting at these faint smudges, and suddenly JWST turns on the high beams.
That's a great analogy. So what were we seeing with those smudges, and how has JWST changed things? What did Hubble reveal about those early galaxies?
Well, Hubble showed us that the early universe was a very different place than the one we see around us today. The galaxies back then were smaller, clumpier, more chaotic.
Less like the grand spiral galaxies like our own Milky Way.
Exactly. They seemed to lack that elegant structure. Astronomers thought it took billions of years for galaxies to settle into those spiral shapes.
So before JWST, everyone thought spiral galaxies were a later development in the universe's timeline.
Right. It's like comparing a newborn baby to a grown adult. They look completely different, right? Astronomers figured galaxies went through a similar kind of growth and development over billions of years.
So where does JWST come in? How does it give us a clearer picture?
It's all about the type of light it can see. JWST is optimized for infrared light, which is crucial for observing very distant objects.
Okay, so light. What's so special about infrared light? And why is it so important when we're talking about seeing the most ancient, distant objects?
Imagine you're trying to look through a thick fog. It's hard to see anything clearly, right?
It's super blurry, yeah.
Well, observing the early universe with visible light can be kind of like that. You see, the early universe is full of dust and gas, and this stuff can block visible light, making it hard to see what's behind it.
Ah, so it's like the dust and gas are creating a cosmic fog.
Precisely. But infrared light, which has a longer wavelength than visible light, can cut through that fog much more easily. It doesn't get scattered as much by the dust and gas.
So we're talking about the same universe, the same objects, but the way we observe them with different types of light can reveal totally different information.
Exactly. Think of it like this. Imagine you have a basket of fruit, but you're wearing a pair of glasses that only let you see red light. You'd only see the apples, right?
Makes sense.
But if you put on a pair of glasses that let you see green light, suddenly you'd see the pears and the grapes that were hidden before.
So JWST is like putting on those special glasses that reveal a whole hidden layer of the universe.
That's a great way to put it. And not only that, But the light from those incredibly distant galaxies has been stretched as it travels through space for billions of years, shifting towards the redder end of the spectrum. This effect, called redshift, means that to see those early galaxies, we need a telescope that can see infrared light. That's where JWST comes in, giving us an unprecedented view of the universe's infancy.
So it's like we've upgraded our cosmic lenses.
Exactly. And one of the first things JWST set its sights on was a galaxy cluster called SMACS 0723.
I've seen that image. Absolutely breathtaking.
It really is. And it's not just a pretty picture. This cluster is so massive that it actually acts like a giant magnifying glass in space.
Wait, a magnifying glass? How does a cluster of galaxies act like a magnifying glass?
It's all thanks to Einstein. Well, his theory of general relativity, at least, it's a phenomenon called gravitational lensing.
Okay, I've heard of that. But honestly, it's one of those space things that always makes my brain hurt a little. Can you break it down for us?
Sure. Imagine you've got a bowling ball on a trampoline.
Okay, I'm picturing it.
That bowling ball represents a massive object in space, like a galaxy cluster. Now, if you roll a marble across that trampoline, what happens?
It doesn't go in a straight line, right?
Right.
Because the bowling ball warps the fabric of the trampoline.
Exactly. And it's the same thing with light and gravity. Massive objects warp the fabric of space-time around them.
Space-time. There goes my brain again.
Don't worry, the analogy still works. The point is that warping caused by gravity can bend the path of light as it passes by.
So the light from those more distant galaxies behind the cluster, it gets bent by that warped space-time.
Exactly. And not just bent, it gets magnified too, making them appear brighter and larger than they would otherwise.
So it's like the galaxy cluster is giving us a helping hand, allowing us to see those incredibly faint and distant objects.
Exactly. It's a cosmic gift from Einstein. And that brings us back to the panic at the distance paper.
Right. Those astronomers use this gravitational lensing effect to get a closer look at those early galaxies. And that's where things took a surprising turn.
You could say that again.
So before JWST, the prevailing wisdom was that these early galaxies were mostly small and clumpy, like cosmic building blocks that hadn't quite formed into anything grand yet.
Right. They thought galaxies took billions of years to evolve into those majestic spirals we see today.
But then JWST comes along and basically says, hold my beer.
Pretty much, because what did they find when they looked at those early galaxies with JWST?
They found a whole bunch of galaxies that look surprisingly dot-organized.
Exactly. A surprising number of those early galaxies had distinct disk shapes, the kind you need to form those beautiful spiral arms.
So those graceful spiral structures that we thought took billions of years to emerge.
They were already there just a few billion years after the Big Bang.
That's like looking through a time machine and seeing a bustling metropolis in a time when everyone thought settlements were still just tiny villages.
That's a great way to put it. It was a huge shock to astronomers. They weren't expecting to see such structured galaxies so early in the universe's history. Hence the title of the paper, Panic at the Disks.
Okay, I can see why astronomers were freaking out a little. I mean, this throws a wrench into our whole understanding of how galaxies evolve, right?
Absolutely. I mean, think about it this way. Imagine you walk into a bakery expecting to see a bunch of simple dough rising, maybe some basic bread in the oven.
Yeah, I'm with you.
But instead, you open the oven and find a bunch of perfectly formed croissants, already golden brown and fleeky.
And you're like, hold on, how did those get there so fast?
Exactly. That's kind of what it's like with these early disk galaxies. We thought it took billions of years for galaxies to go from those messy, clumpy structures to those elegant, organized spirals.
And just to be clear, it's not just that spiral galaxies look prettier, right? There's a reason why finding these disks so early in the universe is such a big deal.
Right. It's not just about aesthetics. Spiral galaxies are thought to be signs of a more mature, evolved galaxy. They form in a different way.
So how do they form? Why is that spinning disk structure so important?
Well, those early clumpy galaxies we talked about, they're kind of like cosmic demolition derbies.
Lots of collisions.
Exactly. Lots of smaller galaxies smashing together. Things are chaotic. But to form a spiral galaxy, you need a more stable environment.
So things calm down a bit, the cosmic dust settles.
Exactly. Over time, gravity pulls all that gas and dust into a rotating disk. And that rotation, that's key. It's what gives spiral galaxies their shape, and it also plays a big role in star formation.
So all those beautiful spiral arms we see in images of galaxies like our own Milky Way, those are a result of that spinning disk.
Exactly. Those spiral arms are like traffic jams for gas and dust. Everything gets kind of backed up in these dense regions, and that's where you get a lot of star formation.
So finding all these well-formed disk galaxies in the early universe, it's like finding evidence of complex life forms in the fossil record way earlier than we thought possible.
Exactly. It's a sign that maybe, just maybe, our timelines for how galaxies evolve have been way off.
Okay, so what now? What are the astronomers behind this panic? At the Disks paper, what are they saying about what this all means?
Well, for starters, it means we've got some more thinking to do.
Because clearly something isn't quite adding up.
Right. Either those early galaxies found a way to settle into those disk structures much faster than we thought possible, or maybe there's something else going on, some process that we don't fully understand yet that can speed up the process of galaxy evolution.
It's like the universe is throwing us a curveball and saying, figure this out.
Pretty much.
Yeah.
But that's what makes astronomy so exciting. Every new discovery leads to more questions, more mysteries to unravel. And with JWST, we finally have the tool to start finding those answers.
It's incredible to think that we're living in a time when we can peer billions of years into the past and uncover secrets of the universe that have been hidden for all of human history. Who knows what other surprises await us out there in the vastness of space? That's all the time we have for today's deep dive into the fascinating world of galaxy evolution. We'll keep you posted as new discoveries are made. Until then, keep looking up.
You wanted to hear about some of the latest discoveries coming from JWST, right?
Absolutely.
Well, get ready, because we are diving deep today into a research paper, and this one is really flipping our understanding of the early universe on its head.
Yeah, what's so cool about this paper is that it's based on, those very first images from JWST.
Right.
And it shows something totally unexpected.
Okay.
We're seeing like a really surprising number of disk galaxies, like those classic spiral shapes.
Right.
Like our own Milky Way, much earlier in the universe than anyone thought possible.
So wait, we're talking about galaxies like ours billions of years ago, already formed, already in these like structured shapes.
Exactly.
That seems kind of counterintuitive if the early universe was just this chaotic soup of newly forming stars.
Yeah. You would think,
Yes.
right. That was kind of the prevailing theory. So this paper looks at observations of the SMACS 0723 galaxy cluster,
Okay.
which has been studied quite a bit with Hubble.
Right. SMACS 0723, that cluster of galaxies all hanging out together. I remember those images. They were stunning.
Beautiful.
But JWST just takes it to a whole new level, doesn't it?
Oh, absolutely. It's
Yeah.
like this. Think of Hubble like trying to figure out what a building looks like by just looking at its lights at night.
Okay.
You get a sense of where it is, but not much detail.
Right.
JWST, it's like seeing the building in broad daylight.
Okay.
And we call this seeing the rest frame optical light.
Okay.
And suddenly we can see the walls, the windows, like the whole structure.
Wow.
This is why JWST is such a game changer.
So Hubble gave us a little sneak peek, but JWST is like pulling back the curtain, revealing these early galaxies in all their glory.
Totally. And what it's showing us is really challenging a lot of our assumptions about how galaxies form. See, astronomers expected to find mostly those irregular, chaotic galaxies in the early universe,
Right.
which makes sense based on what we knew from Hubble and those theories about galaxies forming through mergers.
Right. It's like a cosmic mosh pit, everything colliding and merging.
Yeah. But instead of a mosh pit, we found a bunch of these like beautifully structured disk galaxies just hanging out, already formed,
Really?
at a time when the universe was practically a baby.
Wow.
It's crazy.
Okay, so what did those early galaxies actually look like through JWST? How did those images compare to what Hubble saw?
Well, the paper actually shows a side-by-side comparison of images taken with Hubble and then with JWST, and the difference, it's pretty amazing.
Okay, but like, give me an example. What am I seeing?
Okay, so picture this. You're looking at, say, a Hubble image.
Okay.
You might see a faint fuzzy blob.
Okay.
It's really hard to tell what you're even looking at, no clear shape or structure.
Right.
Then you look at the JWST image and bam,
Yeah.
it's like, whoa, beautiful spiral structure.
Wow.
Almost like you're looking at a totally different galaxy.
That's incredible. It's like those before and after photos, but for galaxies billions of years old. So these galaxies are just hiding in plain sight. And JWST has like X-ray vision or something.
Yeah, exactly. It's wild. It's seeing right through all that cosmic dust and gas and showing us, like the bare bones, the structure of these galaxies.
Wow.
And it's not even just like pretty pictures, right?
Right.
The researchers here used some pretty hardcore analysis techniques to quantify what they were seeing.
Okay, well, let's dig into that a bit. What kind of analysis are we talking about here?
Sure. So one thing they measured is called a STScI index.
STScI index.
And it's kind of like this. Imagine you're looking at a city skyline,
Okay.
a city with a ton of skyscrapers, all clustered together in the center.
Right.
That would have a high STScI index. All the light is concentrated in one small area.
Okay.
But a city that's more spread out, with a mix of buildings and parks, that's going to have a lower STScI index.
Gotcha. Okay. So what did these early galaxies look like? High-rises or sprawling suburbs?
Well, they found that a lot of these early disk galaxies had STScI indices that were more like that spread out city, which lines up with what we'd expect to see with disk galaxies. Basically, the data backs up what they were seeing visually. These early galaxies were surprisingly structured.
Okay, so we've got the images, we've got the analysis. Everything's pointing to the fact that, yeah, disk galaxies, they were present in the early universe. But that kind of throws a wrench in things, doesn't it? I mean, how can these, like, delicate structured galaxies even form in what we thought was this chaotic, merger-filled early universe?
Yeah, that's the million-dollar question, right?
Right.
It really does challenge our whole understanding of how galaxies evolve.
Yeah.
Because like you said, the thinking was that these early galaxies were constantly smashing into each other.
Right.
Which you'd think would make it basically impossible for these stable disk-like structures to survive.
Right, like trying to build a sandcastle in a hurricane. So what are people saying? How could these early disk galaxies have pulled it off?
Well, there are a couple of ideas out there. One possibility is that maybe those early mergers, they weren't as violent or as frequent as we thought. At least in the areas where these disk galaxies were forming.
So maybe these disk galaxies just got lucky, found a little cosmic safe haven to do their thing.
It's possible.
Yeah.
Another idea is that maybe these disk galaxies did go through mergers, but they were able to kind of bounce back really quickly, reform those disk structures.
Interesting.
And there's actually been some simulations that show that, yeah, this super fast disk reformation, it's possible.
Wow. So these disk galaxies were tougher than we thought, like cosmic survivors.
Yeah. And that makes you wonder about the conditions in the early universe, what was going on back then that allowed for galaxies to form so fast to make these really resilient structures.
Yeah.
These are the questions that are going to keep astronomers up at night for years to come.
Yeah.
And it makes you wonder, could our own Milky Way have been one of these early bloomers?
It really is mind-blowing to think that our Milky Way, this massive galaxy that we live in, could have started out that way billions of years ago.
Right, like a cosmic veteran, just holding on to that structure for eons. And if so, what does that tell us about, like, the universe's evolution? But, I mean, we need more data to really know.
And that's where the next chapter of the research comes in, right? What are the next steps here? What do astronomers need to do to, like, really figure out what's going on with these early galaxies?
So this paper, it's just a small piece of the puzzle. Remember, they were looking at a really tiny, like a teeny tiny corner of the universe.
Right.
So to know if this whole abundance of early disk galaxies, if that's true everywhere, astronomers are going to need to use JWST to observe a much wider area.
So zoom out a bit and see if we find more of these early bloomers hanging out in other galaxy clusters.
Exactly. It's like if you find a rare flower in your backyard, you don't know if it's truly rare. You got to go check out other fields, other gardens,
Right. That makes sense. So are there any plans in the works to do that kind of large-scale, like, cosmic exploration with JWST?
Oh, absolutely. There are already a bunch of these big JWST surveys in the works, which is super exciting. These surveys will give us a way bigger sample of early galaxies to study, to confirm these findings, and hopefully answer some of these big questions.
That is exciting. Okay, well, before we wrap up our deep dive into these early galaxies, I'd like to leave our listeners with something to really ponder. We've been talking about how mysterious it is that these disk galaxies could form so early on. But what do you think this tells us about the conditions in the very early universe? What was happening back then that allowed these, like, delicate, seemingly delicate structures to arise out of what we think of as this chaotic soup after the Big Bang?
Yeah, it's such a good question, and I don't know the answer.
Right. It's kind of a mind-blowing thing to think about.
It really is. It's
Yeah.
going to keep not just astronomers, but hopefully some of our listeners thinking for a long time.
It's really incredible, and it is such an amazing time for discovery.
Absolutely.
I can't wait to see what we learn next. Thanks for joining us for this deep dive.
Thanks for having me. All right, everyone. So we're diving deep into early galaxies today.
Yeah.
A topic I know a lot of you have been asking about.
Yeah.
And with this new data from the James Webb Space Telescope, things are, to put it lightly, weirder than we thought.
Yeah, it's some pretty wild stuff. This JWST data, it's really like getting a new prescription for our puzzle pieces.
Before this, it was like, I don't even know. Trying to understand the first galaxies with like a busted flashlight. I mean, we had Hubble, of course.
Right. Limited.
Yeah.
It could only see so much with the wavelengths. It was limited to.
Mm-hmm. So what did you think you were going to find when you pointed this like super-powered telescope at these early galaxies?
Honestly, more of the same. You know, we had Hubble showing us all these kind of blobby, clumpy galaxies just smashing into each other constantly.
Well, it's chaos.
Yeah, we thought it was just going to be more of that.
So what happened when the data started coming in from JWST?
Well, it really flipped the script.
Okay, come on.
Yeah.
Spill the tea.
All right, so we're looking at this new research called Panic at the Disks.
Okay, first of all, best research paper title ever.
But seriously, why the drama?
Well, these disks, they're a sign of a more like a structured, organized galaxy. Spirals, like a young Milky Way, that kind of thing. And they were everywhere.
Wait, hold on. You're saying the early universe, like right after the Big Bang, was organized?
It seems that way, yeah.
I thought it was supposed to be a free-for-all out there.
That's what we all thought. But this data from JWST, it doesn't lie. They found something like 10 times. 10 more disk galaxies than anyone expected.
10 times. Okay, that's not just like a little adjustment to the theory. That's like throwing the whole textbook out.
Yeah.
Were they looking in the right place?
They were looking at the SMACS 0723 field, which is a region of space, with really reliable distance measurements.
Okay.
So it's kind of like a cosmic ruler, helping us pinpoint exactly how far back in time we're looking. Gotcha. So they're looking at the right stuff. They've got the right cosmic ruler. How do they explain all these surprisingly structured galaxies?
Well, that's where the real mystery begins.
Oh, you can't leave me hanging like that. Give me the theories. Why is the early universe more like
a well-choreographed dance than a mosh pit? All right, so we've got a cosmic mystery on our hands. Too many organized galaxies, not enough chaos. So what are the leading theories here? What could explain this?
Well, there are a couple of possibilities. One idea is that these early disks were somehow able to survive, billions of years of mergers without getting totally scrambled. Hold up.
Really? Yeah. Surviving cosmic billiards for billions of years? That seems, I don't know.
It's wild.
It's tough.
It's remarkable to think about. Yeah. Like finding, I don't know, like a perfectly preserved antique in your grandma's attic. You have to wonder how it survived this long in such good shape.
Totally. Okay, so what's the alternative? Because honestly, pristine antiques in space are stretching my imagination a bit. Okay, so get this. Some galaxies might have actually gone through mergers. But then, get this, reformed their disks afterward.
Reformed? You mean like a cosmic reset button for galaxies?
Kinda.
Smash them together, pull them apart, boom, good as new.
In a way, yeah. The paper we're looking at actually points to some simulations that back this up.
Okay.
It turns out that when gas-rich galaxies merge, they can sometimes trigger the formation of a brand new disk structure.
So it's not just about surviving the mosh pit, it's about knowing how to like shake it off and get back to that structured galactic groove. That's wild. But if we're being honest here, we're working with a pretty small sample size, right? It's just one little patch of sky.
That's true. Yeah, you're absolutely right. It's like trying to understand the entire history of Earth by studying your backyard. We need a wider view.
Totally. Yeah. So what happens now? What are the next steps to figuring this whole thing out?
Well, more observations with JWST, of course.
Of course.
We need to see if this trend of well-behaved galaxies holds true across a much larger chunk of the universe.
Larger surveys. Makes sense. But even with this like initial glimpse, it feels like JWST is totally rewriting the early chapters of cosmic history.
It really is. And remember, spotting these disks, that's only the first step. Now astronomers can use JWST's instruments to really analyze the nitty-gritty of these galaxies.
The nitty-gritty, like what?
Talking about what kind of stars they have, how much gas they contain, how everything is moving inside them.
So it's like, we found this new species, but now we need to understand its whole deal. It's like its life cycle, its diet, the whole shebang.
Yeah, that's a great way to put it. And by digging deep into these early galaxies, we might uncover even more clues about how the universe and our own galaxy came to be.
Okay, so much to learn, so much to explore. But before we get too far ahead of ourselves, are there any caveats from the research that we should keep in mind? Anything that makes us say, hold on, not so fast. So are there any cosmic speed bumps we should be watching out for here? Any reason to pump the brakes on this whole orderly universe idea?
Well, it's important to remember that we're still in the early days of analyzing this James Webb data. I like to think of it like finding a treasure chest. We've popped it open, gotten a glimpse of the wonders inside, but there's so much more exploring to do.
Okay, so what are we missing?
Well, for one thing, this study really focused on galaxies that are, pretty massive and bright, like the cosmic heavyweights, the ones that are easiest to see from far away.
Right.
It's possible that fainter, less massive galaxies, ones we haven't really gotten a good look at yet, might tell a different story.
So there might be a whole hidden population of galaxies out there.
With different backstories.
Different evolutionary paths.
Exactly. And while this study, makes a strong case for these surprisingly structured early galaxies, we always have to be open to, other factors that could be influencing what we're seeing. We're talking about a time period that's still shrouded in mystery. It's possible there are processes, forces, maybe even stuff we don't even know about yet that could be playing a role.
Okay, so more research is needed.
Right.
Classic scientist answer. But I have to ask, you mentioned earlier that this discovery could change our understanding of. Like when the very first stars ignited, when the universe truly lit up. Can you explain that? Because that's seriously blowing my mind right now.
Yeah, so it all comes down to timing. If these surprisingly mature galaxies already existed this early in the universe's history, it could mean that the timeline for everything gets pushed back. Like the very first stars, the very first light. It might have all happened sooner than we ever imagined.
Wow. So not only is the early universe more orderly than we thought, but it also might have gotten started a lot earlier than we thought. That's a lot to process.
It is, but that's the beauty of science, especially astronomy. Just when we think we're starting to grasp the universe's grand design, a new discovery comes along, turns our assumptions upside down, and it opens up this whole new set of questions.
And in this case, it's all thanks to this incredible James Webb Space Telescope.
Yeah.
It's like we've had this incredible cosmic library right at our fingertips. And now we finally have the key to unlock its deepest secrets.
I love that analogy. It's so true. JWST is a game changer. It's a revolution in our understanding of the universe. And this discovery about early galaxies, it's just a taste of the incredible things to come.
Okay, so as we kind of wrap up this deep dive, what's the one big takeaway you want our listener to walk away with today?
I think it's this. Never underestimate the universe's capacity to surprise us. What we thought was a chaotic free-for-all in the early universe might actually be a carefully choreographed cosmic dance. And with JWST as our guide, we're only just beginning to learn the steps.
Beautifully said. And on that note, a huge thanks to our expert for taking us on this incredible journey through the early universe.
Oh, it's my pleasure as always. The universe is full of mysteries, and it's always a thrill to explore them with you.
And to you, our listener, thank you for joining us on this mind-bending adventure into the depths of space and time. We'll keep diving deep, keep asking questions, and keep uncovering the wonders of the cosmos together. Until next time, keep looking up. So you're interested in the early universe, huh? Trying to picture those very first galaxies. Were they like the majestic spirals we see today, or something completely different?
It's a question that's kept astronomers up at night for a long time. Yeah, and thanks to some amazing new data, we're getting a clearer glimpse of what those early galaxies were really like.
And let me tell you, what we're finding is turning everything we thought we knew upside down. Get ready to dive into some groundbreaking research based on the James Webb Space Telescope, the JWST. It's changing everything.
It's true. The JWST is giving us an unprecedented look back in time, billions of years further than we've ever seen before.
The paper we're diving into today has a pretty dramatic title, Panic at the Disks. First rest frame optical observations of galaxy structure at Z3 with JWST in the SMACS 0723 field.
That catchy, isn't it?
Definitely grabs your attention. So what's got everyone in a tizzy? This research focused on a distant cluster of galaxies called SMACS 0723. We're talking really old galaxies here, some of the first to form after the Big Bang, over 12 billion years ago. And what the JWST revealed about these galaxies was completely unexpected.
For years, the Hubble Space Telescope was our main window into the distant universe, and it gave us some incredible images. But the JWST. The JWST is like putting on superpowered glasses. We're seeing things with clarity we could only dream of before.
So before we get into the mind-blowing discoveries, let's set the stage. We need to talk about the Hubble sequence. This is how astronomers classify galaxies, right? Kind of like putting them into families based on their shapes.
Exactly. You've got your graceful spirals like our own Milky Way, your more rounded ellipticals, and the ones that never quite made up their minds, the irregular galaxies.
So imagine a family photo album of galaxies. You'd see those classic spirals, the ellipticals looking a bit more like cosmic balloons, and then the irregulars, kind of the free spirits of the bunch.
That's a great way to think about it. Now, before the JWST, astronomers thought that these very early galaxies were mostly irregular, still kind of messy and undefined in their structure. The idea was that the elegant spirals, like our Milky Way, evolved much later in the universe's timeline.
So it's like looking at baby pictures. You might get a hint of who they'll grow up to be, but they're still developing, still figuring things out.
A good analogy. But here's where the JWST throws a cosmic curveball.
Hold on to your hats, because here's the jaw dropper. The JWST found way more spiral galaxies in those early galaxies than anyone ever imagined. Like, way more than we thought possible. We're talking up to 10 times more.
And that's not just a slight miscalculation. This discovery throws a wrench into our whole understanding of how galaxies form and evolve. We thought those early galaxies were mostly chaotic blobs, slowly merging and evolving over billions of years to form those majestic spirals. But
Now it's like finding a bunch of perfectly formed snowflakes in the middle of a summer heat wave. It makes you question everything you thought you knew about how snowflakes form.
it really does make you rethink things. The very existence of these early spirals suggests that maybe, just maybe, some galaxies were born with that elegant structure. They didn't need billions of years of collisions and mergers to get it right.
Okay, this is already blowing my mind. But before we get lost in the vastness of it all, let's zoom back in for a second. How could they be sure these blurry blobs billions of light years away were actually spirals? Was it more than just a cosmic hunch?
Excellent question. And the answer is a resounding yes. They didn't just glance at a few fuzzy images and call it a day. They used some pretty incredible techniques to confirm what they were seeing.
Okay, you've got my attention. Tell me more. How do you go about measuring the shape of a galaxy that's been around since the dawn of time?
Well, there are a couple of key methods they used. First, they visually examined the high-resolution images from the JWST. Expert astronomers literally scrutinizing every pixel, looking for those telltale spiral arms. But it goes beyond that.
So it wasn't just a matter of, hey, that galaxy kind of looks like it's got a swirl to it. There was some serious science going on to back it up.
Absolutely. They went beyond those initial visual checks and used something called quantitative measurements. Think of it like this. You can guesstimate the size of a cake just by looking at it, but a baker will use precise measurements to get it just right.
Okay, so what kind of cosmic measuring tape are we talking about here? How do you measure a galaxy anyway?
They used a few different methods, but one of the key ones looks at how the light is distributed within the galaxy. It's a bit technical, but basically the pattern of light in a spiral galaxy is different from that of an elliptical or irregular galaxy.
So the light itself holds clues to the galaxy's shape even across billions of years.
Yeah.
That's incredible. But here's what really gets me. What does this discovery actually mean? I mean, so we found a bunch of ancient spirals. So what?
That's the million-dollar question, isn't it? And the answer is that it has profound implications for our understanding of the universe. For starters, it challenges the long-held belief that galaxy mergers, those cosmic collisions we always hear about, were the driving force behind the formation of spirals.
Because if those early galaxies were already spirals, then maybe those mergers weren't as common or as essential as we thought.
Exactly. It suggests that spiral galaxies might have been far more prevalent in the early universe than we ever imagined. And that in turn could mean that the conditions for stars to form and galaxies to evolve were quite different in those early days.
You know, it's like realizing that the history books got it all wrong.
Yeah.
We thought we had this linear progression figured out, but now we're finding out that the reality was much more nuanced, much more surprising. But okay, let's bring this back to our own cosmic neighborhood. If these early galaxies really were spirals, what does that tell us about our own galaxy, the Milky Way?
Now that's where things get really interesting. You see, if these ancient spirals formed in a way that's similar to how we think the Milky Way formed, it could mean that our galaxy has looked more or less the same for billions of years.
Billions of years with those graceful spiral arms, that iconic shape. That's mind-blowing. You mean those early galaxies, some of the first ones to light up the universe, might have looked like miniature versions of our own Milky Way?
It's a possibility, and it's a tantalizing one. It makes you wonder if there were other civilizations out there on planets orbiting those ancient stars looking up at a night sky not so different from our own.
Okay, now you're just messing with me. But seriously, it's awe-inspiring to think about. It makes you realize that we're just a small part of this vast, ancient, and ever-evolving universe.
Yeah.
And the more we learn, the more we realize how much more there is to discover.
Yeah.
So where do we go from here? Is it time to toss out our astronomy textbooks and start over?
Well, not quite. That's the beauty of science. It's always evolving. Every discovery leads to new questions, new avenues to explore. This research with the JWST has opened up a whole new chapter in our understanding of the early universe. But it's just the beginning.
So what are the next steps? What are astronomers most eager to figure out about these early spirals?
One of the biggest questions is whether this abundance of spirals is consistent throughout the universe, or if we just happen to catch a glimpse of a very special cosmic neighborhood in the SMACS 0723 field. Think of it like this. You might find a field full of wildflowers, but that doesn't mean the entire planet is covered in them.
So we need to zoom out, look at other parts of the sky, and see if those early spirals are everywhere or if we just got lucky with our first peek.
Exactly. And the JWST is perfectly suited for that. It's going to be surveying vast regions of the cosmos, peering further back in time, and giving us a much wider perspective on the early universe.
It's like we've just opened the first page of a thrilling mystery novel. We've got a few tantalizing clues, but we're dying to know what happens next.
And the best part is, we're living in a time when those answers are within our reach. The JWST and other powerful telescopes are rewriting our understanding of the universe, and it's an incredibly exciting time to be an astronomer.
You know, it's humbling, isn't it? To think that for centuries, humans have looked up at the night sky and wondered about those distant points of light. And now we're finally starting to unravel some of their secrets.
It really puts things in perspective, doesn't it? We're just beginning to scratch the surface of what's out there.
Well, I, for one, can't wait to see what other surprises the universe has in store for us. And on that note, I think it's time to wrap up this deep dive.
Indeed. Always a pleasure exploring the cosmos with you.
Until next time, keep looking up and never stop questioning what lies beyond our world.